Okay guys, we are here for the first lesson of Unit 2. Unit 2 is all about polynomial functions and their equations and polynomial inequalities. So today's topic is well, it's a bit of a long one, but today we're going to focus on dividing polynomials, and then we will take a look at what the remainder theorem is. These two things are very, very closely related. We need to use the remainder theorem to help us understand what to divide our polynomials by. And so over the next two lessons, we'll make the connection between these two topics. So your goal is that you can divide polynomials using long division or synthetic division. I will show you the methods for synthetic division in a second video, and that you can state your answer in quotient form as well as a division statement. We might look at quotient form briefly, but we'll mostly focus on the division statement. Okay, so in order to do this, we need to have a little refresher of long division. And so for some of you, it's maybe been a very long time since you've done long division. So here we have 62,345 divided by 15. And if we had a calculator, we could very quickly divide these. That would not be a problem. But if we wanted to do long division, we have to remember how to do this. So we're looking at this and we see that 15 does not go into 6 at all. So we would, in theory, have a 0 here. We just leave it blank. So then we move over and say, okay, well then how many times does 15 go into 62? Well, we know 15 goes into 30 twice, and then that's double. And so 4 times 15 can go into 62. And then we do our 4 times our 15, and we put that number here, and that's 60. And then we draw a line and we subtract. So we have 62 minus 60, and we have a 2 here, and we bring down our 3. So now we're looking at, okay, how many times does 15 go into 23? And it can only go in 1 time. So now we're doing 1 times 15 over here. And again, we are subtracting. And so now we have 23 minus 15, which is 8. And then again, we bring down our 4. And now we're thinking, okay, how many times does 15 go into 84? So it went into 64 times. If we add 15 to that, that would bring us up to 75. That's as many as we can get into 84. So we're going to put a 5 here, and 5 times 15 is 75. And again, we're going to subtract these and be left with a 9, and then we're going to bring down that 5. And now, how many times does 15 go into 95? Well, it can go in one more time now. We knew that 5 times was 75, so 6 times would be 90. And then again, we subtract, we're left with a 5. There's no other number to bring down, so we are done. So this here, the number that we're trying to divide, is called our dividend. And the number we're dividing it by is called our divisor. And the number of times the divisor can go into the dividend is called the quotient. And whatever is left over is called the remainder. So some terminology that you've probably heard before but maybe haven't looked at in a while. So we divide a dividend by a divisor. However many times the divisor goes into the dividend is the quotient, how many full times, and then however whatever is left over is called the remainder. So using that, we could write a division statement. So we could take some of the information that we have up here and rewrite it as a division statement. So the divisor multiplied by the quotient, so in this case we have 15, multiplied by 4,156, plus that 5 that was left over, is equal to 62,345. Okay, so that's our division statement. The divisor multiplied by the quotient plus the remainder is equal to the dividend. We could also do the dividend divided by the divisor. Okay, so divided by the divisor is equal to the quotient plus, if we wanted to represent this as a decimal, the actual answer would be 4,156, and then there would be a decimal here, and it wouldn't be 0.5 because it's not half. It would be the decimal that is equivalent to 5 over 15, which is 1/3, which would be 0.33 continuous. So it would be the quotient plus the remainder divided by the divisor. And that is our quotient form, and we're not really going to deal with it as much, but if you do come across it, that is our quotient form. But our division statement we are going to use a lot. Okay, so if you don't remember long division, you might want to play around with that. You can divide anything, especially if we're allowing remainders, like choose a number, 75,412 divided by 22. Okay, like pause the video right now if you want, play around with that. Play around with that method of how many times the multiplying, the carrying down, so on and so forth. All right, so now, because now things are going to get funky, now we're actually going to be long dividing polynomials, and the process is actually quite similar as it is for just dividing numbers, but if we're still not confident here, then we might want to practice that. But we're going to jump right into dividing polynomials. So some things to know. The polynomial must be in descending powers of x. So for example, this has x to the power of 4 first, and then x to the power 3, x to the power 2, x to the power of 1. We don't write the 1. And then x to the power of 0. Again, we don't write x to the power of 0. But this is in descending powers. All powers of x must be accounted for, meaning we have 4, 3, 2, 1, and 0. If any of the powers were not accounted for, we'll look at an example next, then we have to put in a placeholder for them. So if, for example, there was no negative 30x here, we would have to put 0x, but we'll look at an example. And you'll know that you're done when the degree of the remainder, so that thing at the bottom, is less than the degree of the divisor, but we'll get to that. The degree of the divisor right now, this is degree 1, and so we will know we are done when the remainder is degree 0, or in other words, a constant. So, okay, how does this go? We are trying to figure out how many times does x go into 3x to the power 4. Now, when we think about this idea of going in, how many times does it go in, I find it really helpful when we're long dividing polynomials to think about, what do I need to multiply x by to get 3x to the power 4? Well, I would need to multiply it by 3x to the power 3. So just to align our powers, I'm going to put this here. 3x to the power 3 is what I would need to multiply by. The first step is always going to be to cancel out these terms, and I'll show you what that means. So we go back, we multiply, we put it underneath. So 3x to the power 3 times x is 3x to the power 4, but we have a binomial here. We're dividing this polynomial by a binomial, so we actually also have to multiply this 3x to the power 3 by the negative 5. So I've got positive 3 and negative 5, which is negative 15, and I have x to the power 3 multiplied by, we don't have any x with powers over there, so we just have x to the power 3. Now the steps are the same. I have to subtract, and the goal will always be these terms should always cancel each other out. If they don't, you've done something wrong. So here we have 0. Now I have negative 12 minus negative 15. So this becomes positive. So I have negative 12 plus 15, which gives me 3x cubes. And now is where I bring down my negative 20x squared, and then we go all over again. What do I need to multiply x by to get 3x cubed? Well, I would have to multiply it by 3x squared. 3x squared times x is 3x cubed, which is great. That's what we wanted. 3x squared times negative 5 is negative 15x squared. We draw my line, subtract. These should cancel out every time, otherwise we've done something wrong. Negative 20 minus negative 15 is negative 5x squared. Then we bring down the negative 30x. How many times does x go into negative 5x squared? Or in other words, what would I need to multiply it by? I would need to multiply it by negative 5x. Now I go back and multiply negative 5x by x is negative 5x squared. And negative 5x by negative 5 is positive 25x. These cancel out, as they should. Negative 30 minus 25 is negative 55x. Okay, so now I have to figure out, okay, what do I need to multiply x by to get negative 55x? Well, I'd have to multiply by negative 55. Negative 55 times x. Oh, sorry, I forgot to bring down my 2. Whoop. Bring down my plus 2. Okay, so multiply these, we get negative 55x. And now I have to do negative 55 times negative 5. So this is going to become a positive, and then 50 times 5 would be 250. 5 times 5 would be 25, so that gives me 275. And then again, I'm subtracting these. So these should cancel out, and then I've got 2 minus 275, which is negative 273. Now, I have nothing else to bring down, and also the degree here is less than the divisor. This was degree 1, this is degree 0, so I'm done, okay? So this is the final answer. And we could write now I think I have it on the next slide, that we could take the results from the previous questions and write it as a division statement, but just because rather than flip back and forth, I'm going to do it on this page right here, not on the next page. So if I want to write this as a division statement, what I know is that 3x to the power 4 minus 12x cubed minus 20x squared minus 30x plus 2 is equal to this thing here, which is our divisor, x minus 5, multiplied by our quotient, 3x cubed plus 3x squared, minus 5x minus 55, plus our remainder, which in this case is minus 273. So if we were to expand this out, if we were to multiply this binomial with this polynomial and then combine our constants, we should get back this exact same polynomial that we began with. And that's one way you could check your work, but obviously that would take you a really long time. But if you were using a graphing calculator, you could enter this in your graphing calculator, and you could enter this in your graphing calculator, and you'd better make sure that you're getting back the exact same function. I could show you guys that on Desmos. We're going to hop on Desmos in a minute, so we will take a look at that. Okay, so just, oh yeah, I had already put it there. Okay, so there we got our answer, and then again, if we expand either side, then we would have the same thing. Okay, so the remainder theorem, what does this have anything to do with this? So, so far all we've looked at is reviewing long division of numbers, applied that long division to polynomials. This is going to take practice. This is a very tricky skill, and if you just went through that and you were like, what the heck just happened, you're going to see me do it a few more times, and towards the end of this lesson in the second video, I'm going to show you a trick to make it a little bit easier, but you know how things go in math. We always show you the full way first. So, what is the remainder theorem? So if a polynomial, we'll call it p at x, is divided by a binomial, we'll call that x minus a. So in the previous example, this would be my polynomial, p at x divided by x minus a, and in this case we have x minus 5. So if these two things were divided, the remainder, which in this example the remainder was negative 273, the remainder of that division could be obtained, we could figure out what the remainder is, by subbing in the value of a into the polynomial. So in this case here, basically what we're saying is if we subbed in 5, now notice how it's not, this is a minus a and we're subbing in a positive a. So we're looking at the actual solution. As you guys know, when we're dealing with factors, if the factor is x minus 5, the solution that corresponds with that is x equals positive 5. So if we subbed in that x equals 5 into this polynomial, we would get back this number right here. Okay, so I believe I already entered this in Desmos. Maybe not. This is a different one. Let's put this in here. So we had 3x to the power of 3. Whoa. 3x to the power of 3 plus 3x squared. No, to the power of 4. Sorry guys, I thought I already had this in here, which would save us some time. Minus 12x to the power of 3 minus 20x squared minus 30x plus 2. Okay, so there's our function f at x. And so if we said, well, what is f at 5? There's that negative 273. Okay, so that's not a coincidence. And then again, if you're wondering, like, why do we care about this? Basically, it tells us what the function value, right? When we sub in any value of x and we get back a function value, it's telling us where does the function lie in terms of our y values at that specific x value. And this really does come in handy when we get into factoring and graphing these larger polynomials that go beyond degree 2. Okay, so for example here we have p at x is equal to x cubed minus 4x squared minus 7x plus 10. If we were trying to divide by x minus 2, or if we were dividing by x minus 2, what would the remainder be? We could find that remainder by subbing in that positive 2 into this function, which is what has happened here. We get a remainder of negative 12. That also means that this function has a y value, or a function value, of negative 12 at this value here. And it also happens to be the remainder if we divide them. All right, so let's look at another example where we don't have all powers accounted for. Okay, so we'll do one more for sure in this video, and then we'll see where we're at. So we've got 6z cubed plus 13 z squared minus 9, and we want to divide this by 2z plus 3. So we have some powers missing here, right? We don't have our z to the power of 1. So when we go to rewrite this, we have to do 6z cubed plus 13z squared plus 0z minus 9. And now we're dividing this by 2z. 2 and z together is poor choice. 2z plus 3. Okay, so we're going to go through the exact same. What do I need to multiply 2z by to get 6z cubed? Well, I need to multiply it by 3z squared. So 3z squared times 2z is going to give me back 6z cubed. 3z squared multiplied by positive 3 is positive 9z squared. I'm going to subtract these. Those should cancel out, otherwise I've done something wrong. 13 minus 9 is 4, so I've got 4z squared. And then how many times do I need to multiply 2z to get 4z? Well, I need to multiply by positive 2z. Positive 2z times positive 2z is 4z squared. 2z times positive 3. Oops, sorry guys, forgot to bring down my 0z's. 2z times 3 is going to give me positive 6z. Again, I do my subtraction. I end up with negative 6z. And I bring down my negative 9. I need to multiply 2z by negative 3. Negative 3 times 2z gives me negative 6z. and negative 3 times positive 3 gives me negative 9. And negative 6z minus 9 minus negative 6z minus 9, I'm taking everything away, leaves me with 0, which is my remainder. So now I've divided a polynomial by a binomial where the remainder is 0. And that's actually our goal, like what we are ultimately looking for. What this tells me, if this here, we can call this polynomial p at x. Now we know that, and again, when we're looking at a factor, if this is the factor, the corresponding z value or 0 would be z equals negative 3 over 2. So now what we know is that p at negative 3 over 2 is equal to 0. And that is kind of really important because if, and at any time, if a polynomial has a function value of 0, if we picture our Cartesian and we picture this as a degree 3, so let's say it looks something like this, it will have function values, right? We're looking at our y values of 0 only at the x-intercepts. So now what we've confirmed is that negative 3 over 2 is a location of one of the x-intercepts, which is pretty cool because we need to figure out the x-intercepts if we're going to graph. So finding that remainder of 0 is ultimately what our goal is. And then again, I have it here in writing. So since the remainder is 0, we now know that the divisor, 2z plus 3, goes evenly into the polynomial, and that makes the divisor a factor of the polynomial, and this is great for graphing. All right, I think I'm going to stop this video just for sake of time. Actually, what I'm going to do is I'm going to put this one here, and I would like you guys to try to factor this polynomial completely on your own. We have x to the power 3, x to the power 2, x to the power 1, so all powers are accounted for, and I will have the full solution for this one at the start of the next video. I won't explain the steps, but I'll have the solution so you can at least check your work. Okay.